Okay, can everyone hear me? Hello? All right. So today we'll learn about independent component analysis. We already did PCA. So you guys will be able to draw some ties between ICA and PCA. So can anyone remind me what PCA was? Yeah, go ahead. Yeah. And what did PCA try to maximize? Basis. PCA tried to maximize the variance, right? And the way we did that was multiplying A by its transpose. That way you get the joint like x1, x2, x2, x1. And then you do the maximization on that. So ICA will be similar. So first of all, you guys remember correlated variables, right? If you see here, like this is the x-axis is burger consumption and y-axis is penguin population. So this makes sense because roughly the number of burgers you consume, the less the population. So you can see that there's a line, right? The one direction in x will tell you the direction of y. So this is what correlation is. Uncorrelation is when it's just a flat line. So knowing about one variable will tell you nothing about the other variable. So the more burgers you consume, it doesn't reflect anything about your average income. What's up? Okay. If you disagree, you can speak up. So uncorrelation, you can see the joint expectation is 0 because there is no inherent relationship between x1 and x2 or x2 and x1 because knowing one does not tell you anything about the other. So it's 0. But the second moments are preserved. So those will be non-zero. So you can do a test. Whenever a matrix is diagonal, you know that the two variables are uncorrelated because the non-diagonals are 0. So a lot of times we have, like in real world settings, we have data that is correlated, right? Like this left one. And you want to warp it or put it through some transformation that makes it uncorrelated, right? So we want to find that T that you see at the top there. And PCA was one method, right? Because you found the perpendicular orthogonal vectors that made them basically like, picture these are the vectors, then it made them like this. So they're orthogonal, right? So yeah, when we do YYT, it will be diagonal. And PCA's byproduct is that the data becomes uncorrelated. So this is a byproduct of PCA. It's not the actual goal. So this is exactly what PCA does, right? You found those axes, those red axes, and then it orients it along that. So then it becomes uncorrelated. So the way it did that is that these red vectors, red lines, are the eigenvectors of the covariance matrix. And it's just a side effect, right? It's not the focus. It's a nice side effect that PCA will decorrelate the data. And you can even see the proof here that if we have X equals USV transpose, every matrix can be decomposed in the SVD, right? So if we let the right-hand side be Y, SVT, then if you do YYT, you'll get SVT, VST, SST, and this is a diagonal. So anytime you see a diagonal matrix, that's your gateway to say that the variables are uncorrelated, right? So through the proof, I think you had a similar problem on homework 1. You can prove that the YYT is in SVD, the uncorrelated. So just to recap, the two variables X and Y are dependent if knowing X gives you something about Y. but it's independent if knowing X tells you nothing about Y. There's that conditional probability rule that P of X given Y equals P of X, because knowing Y doesn't tell you anything about X. So yeah. Okay. So now let's talk about independence. Remember that independence is not the same as uncorrelated. Do you guys remember the difference between uncorrelated and independence? There's one stricter condition in independence. It's basically that the joint probability is the same as the multiplying two of them, P of X, P of Y. So there's a popular problem called the cocktail party problem. Picture two people are talking. Statistical independence is like assuming that P of X, let's say that's me, X is Adnan, Y is Bob. So P of Adnan comma Bob is the same thing as P of Adnan times P of Bob. It's a independence assumption that can be very helpful. And that's the basic idea of ICA, is that at the forefront, we're putting independence assumption, right? We did not do this in PCA. PCA found the eigenvectors that maximize the variance. And as a side effect, it became uncorrelated. But when we enforce this, automatically it becomes uncorrelated, right? Some of you may have heard that independence implies uncorrelation, but uncorrelation does not apply independence. So if I put this strict check at the first criterion, then automatically I'll get uncorrelation. I don't need to enforce it later on. So yeah, independence basically is when the expectation can be distributed like this for everything. So if you find one that's off, then it's not independent. So let's do a poll. It's that one. People on Zoom can see, right? Okay. Okay, is everyone done? This link works, right? It's this one. You just put this with 1003 and then 1. Okay. So I'll go over the answer. You can answer the poll whenever you want. So I'll just reveal them. So the first one is false because PCA's objective is not to decorrelate, right? It's to maximize the variance. The side effect is that you get decorrelated data. So, and then this one should be trivial. We don't put the exponents at the, like this, we just distribute it. So yeah. Okay, so is there any question? That was all a recap. So you should understand what I just told you. Okay. So I'll give some quick intuition behind this. So if you can't see, I will move, don't worry. But let's say we have just like the problem I was mentioning, cocktail party problem. And we have two signals. There's two people talking, we have two signals that's capturing data. So one signal might capture like one person more, like this. And another signal might capture another person talking more. So like this. So I'll move. So it's like an X, but you can see there's two independent sources of data, sort of. So if I ran PC on this, it wouldn't really get me the true representation. It might find something like that because it only cares about maximizing the variance. So it will not get the right axis. Some of you may have thought in your head that we want to find something like this. These aren't perpendicular, but it does a good job separating the data into two. So ICA is this one. We'll go over how ICA works. And PCA is this one. PCA is always orthogonal. And ICA does not have that strict constraint. ICA enforces statistical independence. So two people will not have any joint relation between in this cocktail problem. They'll be independent. So that's just a visual for you. So now that we have this note matrix problem you did on homework 1, you can see here. So you have a spectrogram, you have H and W. And in the PCA, what we tried to do, we tried making this orthogonal. We didn't give much emphasis on H, right? So we want to find the best basis W that explain the data in a meaningful way. And the way we attempted to do that was making this orthogonal, because you don't want one base to be related to another one, right? That's the idea of what we did before. So that's what this is. We enforce this constraint that we want WH, the multiplicative product, right? U is WH. We want WH to be as close to M as possible. That's what that first term is. The second term enforces the orthogonality. So WTW is I. And the solution we did before was, let's just use the eigenvectors, right? That's what PCA is. So this is one way to solve this problem. And oh, this is a sensitive chord. Okay, so with PCA, just to recap, we wanted to make the columns of W orthogonal. That way, there's no relationship between the bases. We don't want one base to explain another. So that's what the idea is. They're the building blocks, and the dot product is like the contribution, like the score that one base has towards the overall music. And then this is something good to know. You think of it like the column of W and H like the row, because a row of H is like the single music. That this will be useful later on. Think of W with columns, H as row. So I don't know if this sound will play. Okay. So pause it. And then once we did the PCA, this is how each of them sound. Like it's all in a row, you can see. Yeah, it's noisy. And then same here. Oh. Is there a question? Okay. So the results aren't good. This is with PCA, right? So like I said before, PCA just decorrelates the data incidentally. It's just a consequence. It's like a nice to have. Because we make the basis orthogonal, so decorrelation already comes. So the thing is, what we want to do is we want to focus like at the forefront, just like how I said over there, that we want to enforce the independence. So let's first enforce a constraint that decorrelates the data. We don't want it to be a side effect. So that, if you think about it, is this, right? You look at these notes, they're independent, because when one peak is up, the other is down. It's roughly independent. So the way you do this is it's the same thing, but now look, you have HHT minus D. So you want that to be a diagonal matrix. If you can enforce HHT to be as close to a diagonal matrix as possible, then you will have done it. So this is the task. Find a matrix B. You already have M. M you can load on whatever numpy. And you want to hit it with a B such that the rows of H become uncorrelated, right? So picture M is like a mix of waves. And once you do a transform with B, the rows become uncorrelated. So we already found that PCA is one, but it's not that good. Are there others? So this is PCA. This is another one, if you think about it, right? It lands like a square. And the reason PCA will not find this is because PCA only cares about maximizing the variance. So you can think about this like a problem. There's many different axes that can solve this problem of decorrelation. This is one of them, this blue one. It's a non-unique solution, yeah. Can you repeat that? Hello?
I said, you're unmuted. I just said you are amazing. I mean, I'm unmuted.
Oh, thank you. Yeah. I'm trying. So you can't see my sweat, but I'm like sweating. Okay, and then, so yeah, that repeats this idea. So what we're basically, like I said before, you're starting at the front and saying that let's enforce independence. That's what this thing is saying. The transcription of one note does not depend on what else is playing. So let's think about like an orchestra. There is a drum and there is a trumpet. So picture like the joint probability of the drum and trumpet is the same as the probability of the trumpet, probability of the drum multiplied together. We enforce independence at the start. So that is what IC is. It's basically like PCA, but we start at the front and say that we're going to enforce independence. And as the byproduct, everything will be okay. So that's this. So let me pause. I know I talked a lot. Do you all have any questions? It makes sense to me, but I know to you, I may be over your head.
What else the dependence of factors?
Dependency vector? Where is that?
Shows the pattern.
Yeah, because each row is like a person talking or an instrument. Like each row is an individual sound. So you don't want one row to be related to another row.
Represents dependence.
Yeah, that's through diagonalization. We'll talk about that. Yeah. So yeah, you can read this. ICA searches through all possible combinations of bases to find the set that makes representations in terms of these bases maximally independent. So we care about independence, right? If somebody asked you the difference between PCA and ICA, you could just say independence, because PCA does not care about independence. It just does decorrelation. But ICA actually cares about maximizing independence. So, second poll. Okay, so does anyone know the answer to the first one? You can just shout it out. False, yeah. And the second one? True, yeah. So just to recap, you can think of ICA like, okay, I'm gonna find the best, there's red and blue here, but I'm gonna find the best one that makes it like that, makes it maximally independent. That's how you think of ICA. Okay, so this is a problem called the cocktail problem. I think even Google asked this when they asked the like non-coding questions. Basically, this is like a party, you can think about it, and two people are talking, right? This is one guy, H1T, and that is the second person. And you can picture microphones like throughout the party. So let me go here. So, you're at some wedding or whatever, and there's microphone here, microphone here, microphone here, and you have 3 people talking. Let's make them square. So you can picture that we want the number of the microphones to be same as number of people, because if it's off, then it'll be like indeterminate. This is an exact solution. So we'll make sure that number of signals is equal to number of people. So you can picture if this guy's talking to him, then this is maybe closer here. And this guy's talking to her, this guy's closer. So they're each picking up waveforms. Like this will probably be something like, and same with these two. And if we align them in like a matrix, we can hit it with a transformation to make them separate. So the cocktail party problem is that we want to basically, this is like a combo of people speaking, M1 and M2, each microphone. We want to find the weights that split them up as much as possible. So H1T, H2T, they're like X and Y in a linear system of equations, and W's are the coefficients. So it's like a linear system of equations. So you can think like, this is how M is, right? It's like a mix, right? It's like me talking, someone else talking on a row. So you want to hit it with a weight matrix such that H becomes independent. So M is a mixed signal, W is the notes, and H is the transcription. H is the independent person talking. So one row of H is one person talking. The second row of H is the second person talking. So H represents speakers, M represents microphones. So you want to find the optimal separation. This is called the cocktail party problem. So we talked about PCA last time. PCA will not be a good answer to this problem. Some of you already probably saw with homework 1 that the separation was not good with SVD or PCA. We need another constraint. So this time we will use ICA to solve this problem. So given only M, we want to find that signal that best finds the separation of data. So you can see here, I have a mixed signal. And then when I hit it with that weight matrix, it becomes nicely delineated. And then same vice versa. If you want to make it mixed, then you will do this. So in homework 2, there was a submit the mixing matrix. That's what W is. Okay, so you have this, and you only care about independence here, so that the rows of H are independent. So, A is the unmixing matrix. This lecture will be useful for your second homework, so make sure you review this after class. Okay. So if we have M is WH, then H can be written as W inverse M, and we can rewrite that as AM. So the first way, this is like a brute force, naive way. We first can just say, okay, we don't care. Let's decorrelate M, right? Let's just find a matrix that makes H diagonal, because when a matrix is diagonal, it's uncorrelated. So we don't care, just for giggles, let's find a matrix that makes it diagonal. So you can do the eigen decomposition of AAT or MMT, but like I said, PCA does not work here. We have to enforce independence at the start. So is there a way we can enforce independence? We know eigen decomposition has that middle diagonal term. So we know the matrix to make it undiagonal. So we want to see how can we do this, right? Now, one thing to note is that it won't work for the Gaussian data. Does anyone want to take a guess why it won't work for Gaussian data? So the distribution of the data cannot be Gaussian for ICA to work. Yeah, go ahead.
Like your like if it's data it's already.
Gaussian data already is like a circular form, right? So if you take rotating it, it's like doesn't matter. Rotating a circle doesn't do anything, right? So unmixing, mixing has no meaning when it comes to circles. So that's why with Gaussian data, this will not work. This will be a question on the quiz for some of you, that which distribution will ICA not work on? That will be this one, Gaussian. Okay, so now let's return. We want to find the axes that enforce independence, right? That's the goal. So a lot of times data is offset, so you have to make it zero mean. So that's pretty simple, right? You just go through each row, find the mean of it, and subtract. That's what this is saying. Just first subtract it so the mean becomes zero. So there's two steps in, this is called phobia. This is problem 2 of your homework. There's two steps. First is decorrelating, then whitening, right? So decorrelating is basically this first arrow when it's rotating and it's becoming axis aligned, right? The axes are not at 90 degrees, the red one. So when I make it decorrelated, it becomes like that. And then whitening makes it normalized. So the sigma, the diagonal, what's it called? The sigma matrix, the inverse is applied to make it square, right? You can think of this like the reverse of SVD, right? SVD, I'll just do it here. So SVD took something like this. Like, let's just do maybe like let's rotate it too. So SVD took a object and like, you already know, right? Like a matrix can be said as U, S, V, T. U and V are rotations, and S is the scaling and stretching of the principal and minor axes. So if I have a data like this, let's just say like that, VT will make it aligned, or yeah. We'll make it aligned so that it's decorrelated. And then I want to make it, I want to make the axes same. So then I will whiten it. This is called whitening. I know you can't see, but it's like this. Basically, this becomes whitened. So now the challenge becomes rotating it back. So I think this is V, this is S. This next part will be the rotation back. This is a bit challenging. But these two steps are called, this is decorrelation, and this is whitening. So you'll see in the next slide that it will be clear. Yeah, so you can enforce the MMT, the joint, this will capture the joint representation, and you can eigen decompose it. That upside down V, that's basically like that sigma term. So if you look at this, right, look at the C matrix. It's the diagonal matrix, the negative 1/2 power times ET, right? Do you guys see how that makes it that rightmost square? Let me see if I can point to it. Yeah, so, okay. This is the original matrix, original data. This diagonal to the negative 1/2 power, that'll make it this. Oh, no, sorry. This E transpose will make it this. And then this, the diagonal matrix, the negative 1/2 power, that'll make it this. So this whitening step, whitening matrix will go from here to here. Right? And the reason is, yeah, go ahead. Yeah. Lambda, yeah.
That's why you're using straight up.
Yes, and do you know what happens when you multiply by a diagonal matrix? Like what effect happens on the data? It stretches the axis. So anytime you multiply by an orthogonal matrix, it rotates it. So this is orthogonal, right? This is orthogonal. So that'll basically rotate it here. The data isn't changed, it's rotated. Then the diagonal matrix will stretch it. The reason we do -1/2 power is because this is the eigenvectors of transpose, right? So you can think of it, these are the eigenvectors squared, but you want to do the inverse of it. So that's why you're doing -1/2. So this is critical in your homework too. You need to do whitening. That's the first step. So this will be this. You have to compute the CM product. Does everyone get whitening? Okay. Yeah, go ahead.
Just can you just clarify again why you take the diagonal matrix to -1/2 power?
Yeah, because MMT, like what is that? It's like the eigenvector squared, right? If you take the eigenvectors of MMT, you're getting it the squared form because MMT, right? That's like M squared. But you want to go from here to here, right? If I actually just multiplied it with the eigenvectors, it would stretch it even more. I need to do the inverse to make it normal square like this. So that's why I take the -1/2 power, because that's like 1 upon, and then the square root. Yeah, good.
These should actually be decorrelating and dividing.
Both, yeah.
Oh, I hear so.
You guys should mute unless you have question. Okay. I think I taught someone something today. So now, okay, so perfect. You got to this point, right? You can think about this like the reverse SVD, right? I have the data already. I'm just rotating it and then making it normalized. Now I have to rotate it back to the square form, right? This is it's not a square yet. It's a diamond almost looking thing. So now this comes the hardest step. This is the probably second step of 4B, that we want to find the matrix B that makes the rows independent, right? So we have this X part. Now we want to hit it with a B to make the rows crystal clearly independent. So like I said before, we don't want B to be like a matrix that screws things up. So we have to enforce that B is unitary, meaning that B transpose B is identity. If this property is there, then you can rotate. The rotation property will be there. Anytime you multiply by a unitary matrix, you rotate the data. If it's anything else, you can actually screw it up. So we want to find a unitary matrix so that the rows of H are uncorrelated. Okay. Oh, does anyone have any question? So basically, whitening took care of these two. It became, it's like messy here. We made it decorrelated. Then we made it standard variance across all dimensions. So we're 2/3 of the step there. Now we have to rotate the square to be like a perfect square. So that's the third step.
In the previous section, in the previous just we have the accent first, which is the stretch, and then we rotate it, right?
Yeah, so this is the opposite. This will be the opposite way. Basically, you have that's the messy form, and you want to make it independent. You can think of this like SVD opposite.
Yeah.
So you guys might have remembered in your probability class about moments. So the first moment is like E of X. What does the second moment capture? Variance, right? What about the third moment? Skew. We don't care about skew. the fourth moment is something called kurtosis. Kurtosis is how much different are the tails of the distribution from the Gaussian one. So if we can make the fourth order moment 0, then we have enforced independence. So this will be the second step of ICA, that we make the fourth order moment 0. And if you think about it, there's a lot of permutations, right? See, this is one fourth order matrix. I, J, K, L are different. This is another one, I and J are same. This is another one that J, K are same. So there's a lot of permutations, and it is annoying. So that's why you only make some of them 0. That way you can enforce something very close to independence. So this is the second step in FOB, that you have to make sure that B is unitary and that the result will have its fourth order matrix 0. Just like how we enforced that in correlation, the second order is 0. Same thing. We're going to enforce that the fourth order is 0. We don't care about the third order because that is variance. We care about the fourth one because that is kurtosis. That will ensure that the data is independent. So there's two things B has to be. Unitary, and when you multiply with X, H has the fourth order moments as 0. Okay, so this, if you guys didn't do problem 2 of the homework, this will probably be the step that will take the most computation power, because you can see here, this looks intimidating, yeah? You do, you multiply 4 vectors and sum them up. So it's like adding a bunch of outer products. So this is the weighted correlation matrix. Note that we don't have H, right? We're just pretending we have H, and we enforce the fourth order to be 0. So is there anything I'm missing here? Yeah.
So the fourth order to be identity rather than 0.
Sorry?
The fourth order matrix must be an identity matrix rather than 0. Meaning cross correlations should be cross terms.
It can be identity or diagonal, right?
Yeah, diagonal. That's right, not 0. Go ahead. Sorry.
Okay, so this is the approach you can see here. And you can see like, this means length of calls H. I think that's a bit misleading. And this is like summing a bunch of outer products. That is D.
So the bubble data actually is the row or the columns in match.
HK is the column, right?
But it is Travis actually.
This will be a number, and this will be a matrix. HTH will be a number, like a magnitude.
So this
And
is just
H-
like your correlation matrix. This is just almost exactly like your correlation matrix. Your correlation matrix is simply going to be the average of HK transpose, right?
Yeah.
This
This
is a correlation matrix, except it's energy weighted correlation matrix. So it's norm HK squared times HK transpose. That's being summed. That's it. Very, very minor change.
I think we should stop. Does anyone have any question? Yeah, go ahead.
So why is it that we weight the relationships? Is that the process?
You want the fourth order moment to be 0.
Yes, but I don't see how it can.
We will get this, yeah. Because this is like you can think of A, I, J, K, M, L. Hold on, let me see. Like this. But here, like in that case, the one I showed you, I equals J. So it's like one of them is squared, and then the other is like HH. Because there's many order of second moments, right? Like second moment can be, a fourth order can be like this. Fourth order can be like that or that. Because you're multiplying 4 random things. So there's many different permutations of 4 things, right? So we do, I think this one, second. We don't do all the fourth order. That would be too much work. We just make some fourth order 0. It'll be clear. I know this is probably the hardest part of the lecture. So once you compute this D matrix, then you can diagonalize it. So with the eigen decomposition, right? So let's look at this. So D can be written like this form. And then remember we said that B is unitary. So when we do it here, then this becomes I. So you get this. And then the B can be pulled out and you get this. And now look at this. This matrix is something messy, but this is, sorry, let me see. So yeah, once you have this form, then you can diagonalize it. And this basically is saying that U transpose will make D diagonal. So you need U transpose here is the matrix you're looking for. Yeah. Yeah, exactly. You can see here, right? Dx can be written like that. So this will make it diagonal because UTU and UTU are I. So you want this one, UT, because that's the right thing to apply to make it diagonal. So B is basically U transpose. So now comes the pseudocode. This is really important for your homework too. The first step we went over, right? First step is whitening. So whitening was doing these two, decorrelating and making the variance standardized. But now the third one is harder. The third one, you have to free up the fourth moment. So you calculate the B term, and then you diagonalize. So make sure you look at this slide. This is, you can take note of it, 67 of 131. So 4B is not perfect. And because we only consider the subset of fourth order moments. If you really want to do all of them, that will be computationally very difficult because like you saw, there's a lot of permutations. So yeah. Now we have a third pole. Is it not working? It's a check mark, so multiple can be true. Okay, so I'll just say it. The first one, it computes the transform makes all fourth order moments independent. No, just a subset of them are independent. The second one, it requires a first pre-whitening step. That is correct. That whitening is those two you see that I drew there. And the transform is the eigenvector matrix of the fourth order moment matrix. No, it's a bit more involved. It's the last one. The transform is the product of the eigenvector matrix of the fourth order moment matrix of the Witten data. Yeah. So the last one is correct. So I think we have a lot of time left. We should go over 4B a bit more. So if you have any questions, please let me know. I can go over it in detail too. Yeah, go ahead.
I'm just trying to make sure I'm not thinking about last stuff.
Mhm.
In ICA, so first, lightning, when first you like to, you try to find the basis from the phase time. Like also scale it, so that's the weird, like lambda.
Yeah.
Which is, I'm saying, by
Lambda the minus 1/2 will do this.
the I composition of the data.
This one. The ET will make it this one, but you notice that the variance is unequal, right? One is longer than the other. So that the upside down V to the negative 1/2, that will make it so that the principal axes are same length. So now the final thing is rotating this to make it a square. And that's the hardest part. That's the fourth order thing I was talking about.
So when you try to rotate,
Independent.
so maybe basis.
The data is independent. Because knowing one about one data won't tell you about the other one. So let's recap it. Blah, blah, blah. So we can do, like, think about it like this. You center M, then you compute the autocorrelation matrix, right? And then this third step is the whitening. That's what I drew there. That you have a data and then you make it so that it becomes like that square. So ET will rotate it on the principal axis, and then the upside down V lambda, the negative 1/2, that'll make it like a square, but rotated. So you have to rotate it back to a square. That's where this comes in. Once you compute this one, E of x squared xxt, then you diagonalize it, right? You diagonalize it via eigen decomposition. And this is what you need to make it diagonal, this one, UT. So you basically hit the whitening matrix with this U transpose, and that is your A matrix that you need. So 1 is on its own, 2 is on its own, 3 to 5 is that, and 3 to 4 is that, 5 to 8 is the last step to basically go from, I'll use this big chalk, go from here to make it like that. So now if I know something here, it doesn't tell me anything about the problem, the second one.
So I remember D should be the sum of multiple, the product of multiple vector multiplication.
D should be an outer product sum. Yeah.
Yeah, but it's still a sum of the outer part.
Yeah.
Like matrices, we work on vectors, don't like matrices which has sums, don't we?
X, in this case, X is like each vector. So this will be a number. This is like 1 by M by 1, right? This will be the opposite of that. M by 1, 1 by M.
Product of the I have two nodes axes.
So you have some bucket.
Yeah, exactly. Yeah. This will be a sum of outer products. This thing. Mm-hmm. And then once you have that, that won't be diagonalized. You have to eigen decompose that here. Then you take this right one. Okay, so this is needed for your problem 2. So you, like I told someone else this, it's like the opposite of SVD, except you don't know US and V. So you have the end product of SVD. Now you have to make it back to the input. That's like how you can think of ICA. Okay. I think everything after this is not needed for the homework. It's for your understanding. You guys know the central limit theorem. So the sum of independent variables will always go towards a Gaussian distribution, right? And And it's even true if the independent RVs are not Gaussian. So even if you have like uniform and I forgot, there's one that starts with a C. If you have like 5 and they're not Gaussian, if you add them up together, they will resemble a Gaussian distribution. So there's this notion of one variable is more Gaussian than the other because one has a stronger sum of 2 non-Gaussian variables and one is just a non-Gaussian variable. So you can make it like a strength sort of thing. How much Gaussian is this variable? So we are revisiting this cocktail party problem. And like I said, you can make it like a linear system, right? So x1, x2, and then the weights are there, and S1, S2 are like the individual people speaking. If you solve this problem alone, you may not get what you want. You have to put the constraints. So that's why I said at the start, you enforce independence. That way you get the right A matrix, right? That's what we were talking about. So, okay. I think this is about some Gaussian thing. Let me just see. Okay, this is, I think, explaining the kurtosis of, this is kurtosis. So this is why we cared about the 4th order matrix, and we wanted to make it 0. So is it okay if I end here, Professor? I think they have enough for their homework at least.
I have a question.
Yeah.
Going back to the distribution of data, this Gaussian distributed inside ICA doesn't work. Is it more like the transforms and have infinite solutions, or is it like no solution?
Infinite. Yeah. But because it just rotates along the circle. And there's no point of that.
Yeah.
Because if I rotate along a circle, it doesn't achieve anything.
Yeah. Other thing is, so if it's a non-unique solution, how do we know the best transform?
That depends on the constraint, right? Because you have to enforce the constraints to get that unique solution. So in this problem, we wanted to make the rows of H independent.
Right.
That's why we got that solution. But there's many ways to solve this, right? Like you can not care. Let's go back to this. This is it. Like, I mean, technically, this is the problem. X equals AS. We want to find the A that makes it separate. So there's many ways to solve it. But if we put some constraints, like making it independent, then you'll get a certain A that achieves that. I think this is explaining the kurtosis. So we want to, maximize the non-Gaussianity. So that is what we mean here. Because the kurtosis is like the tails of the distribution. How much does it differ from a normal one? So if we make that 0, then we can enforce more Gaussianity, right? So, yeah. You can see like if it's 0, it's a normal distribution. If it's 3, it's a bit more spiked because the tails differ. And negative 1.2, that's like almost like a uniform. So that's what this 4th order thing was doing. We maximize the kurtosis of the distribution. And kurtosis is basically computationally difficult, but there's some outliers. And then we have this neg entropy metric. Let me see this. So this is another way to maximize or minimize Gaussianity. The neg entropy will be 0. Sorry?
Like massive.
Gaussian, no, it'll be 0. Entropy is like disorder, right? So Gaussian will be like normal distribution. So it'll be 0. There's like no disorder.
The entropy of like a Gaussian negative.
Depends on the largest possible value with equal variance. I think you'll just have a quiz question on this, so I want to just go over it. But in terms of homework, you guys are good. Like I reviewed everything you need for homework too. So you should ask questions about the earlier stuff I said, if you have any problem. Yeah.
So, there's many types of mutations of the H. Something to.
This one.
So why do we, for example, not that
You're talking about this, right?
talk about the balance of that.
Oh, the fourth order. Okay. Oh, how come we only do some? Is that what you're saying? How come we only make some of them 0?
IJK error.
Yeah, there's many different permutations. See right here? You can do independent or some of them can be same. We basically did the second one.
Why do we only do this?
Because all of them will be too hard. So the second one is more feasible to calculate. If all of them, it'll be computationally expensive, right? I'm making this 0, I'm making this 0. This, making this 0 is sufficient for the problem in this, the problem 2 in your homework.
So why is it sufficient?
I mean, it is a subset of the fourth order. So like technically, if you did all of them, it would be even better. But this alone will unmix it pretty well. Once you play the audio, it will be good.
I see. Thank you. Another question about I saw there's an equation about dividing some columns of batch.
That's length columns.
I see.
It's just the mean, like how you normally calculate the mean.
The meaning of the.
Yeah, that's what that was. Like, you know, in the mean, you divide by the total.
Okay.
It's the same thing.
I see. Thank you.
When this slide is released, I really encourage you to review it. It'll help you with at least 2 problems on the homework too. I just want to make sure you guys are good for the quiz, so let me look. Yeah, you don't need no fast ICA for the homework, so you can review this. I don't think it'll be on the quiz either. But fast ICA has like almost like a gradient descent approach. Yeah. And for fun, you can see like, you guys should check out a code of open source projects. So you can actually look at the Python code for fast ICA in this link. I'll just tell you, you can do poll 4, I'll give you the answer. Because you won't need this for the homework or anything. And you can just check these 2. If there's a quiz question about it, just know that fast ICA is about the Newton's method, and it's real time. That's what online means. It computes it fast ICA, that's the name, through online updating and like a Newton's method approach. You guys remember Newton's method, right? From the last, from a couple lectures ago? Yeah, different. That's a bit slower, but this is the main one you need to know. This one.
online, that means it's like.
Real time. It takes a stream. Yeah. And fast ICA is good in one sense, since it's real time, you can get it as the people are talking, right? So you can strengthen your signal more and more. ICA is like a computation, not real time. Let's see, you guys should know probably this for the quiz. ICA is identifiable up to a sign change and a scaling factor. And ICA has no, oh, right, this is important. So ICA doesn't have that descending rank thing that PCA had. You guys remember? The first column was like important in PCA. ICA, it's not like that. So there's no order. And then let's see, this is ICA is run through this. Let's play the note. That's pretty good, right? So it actually delineated them. So that's pretty good. ICA found the independent signals. So for this, bases in PCA represented the building blocks. So can we use ICA? And the answer is yes. You see, like I showed in that picture a while ago, PCA, it'll find the direction of maximal variance. So it'll be the red one, and it's orthogonal, right? PCA is always orthogonal. But look at ICA, it actually finds like almost like the two separate data sources, right? If two people are talking, they're two different data, right? My voice won't be similar to another person's voice. So ICA finds almost like finds that distinguishing mark between the two. So ICA, you see, it's not orthogonal, but it's independent. It found the two independent data sets. Orthogonality is not that great a thing as people think it is, because it may not align with the data. Okay. And we can just see here, these are ICA faces, those are eigen faces. ICA faces look more real, in my opinion. And you can even use ICA for EEG, the brain signal. So now let's see the PCA solution for the note. This is the Russian anthem. And then let's see it. Right, it's still kind of dirty. And then let's see ICA. Okay, so ICA still did not do that good. And the reason is here. We don't have a notion of the best direction, and we don't have a sense of scaling. So we still need to look more into other ways to separate the music. And notes are not independent, right? So that joint independent assumption we made may not make sense sometimes, especially in this case. It makes sense in the cocktail party problem, but here it's not quite good. So we'll have to see other ways to separate the instruments. And that's it.